Hello guys, this is another tutorial on one of the topics in statics. Okay, in this question we're trying to draw the shear force and the bending moment diagrams for the beam shown in this figure. And by the way, we can see it's problem 786 from Hepler version or the edition, I believe 12. Yeah, it's 12th edition. So let me quickly correct this. It's E. Okay, so what is interesting about this beam? Does it look like the beams we used to see in the examples given in the book? Okay, let's take a look here. We have a hinge at point A, have a roller at B, and we have another roller here at D. See, I skipped point C because point C is the key to the solution. We see a hinge here. Usually what we see is something like this. It's a hinge and a roller, or maybe a fixed end, or maybe an overhanging part, but sometimes we encounter these kind of problems. Okay, the key to this problem is to try to imagine this whole beam A, B, C, D, as two separate beams. How? Okay, first of all, let's try to do this. This is the key. These are the two separate beams, separated by this hinge. So what do I have here? I have a roller at point D. And what do I have here? I have a hinge at point A. Point B, have another roller. Okay, something funny goes here. Okay, here's how you can solve this problem. You can trace another roller here and start doing this part of the problem. We have 5 kilonewton and this length is 3, or it's divided 1.5 and 1.5 meters. So this get distributed equally to D and C. So we have a reaction here that is equal to the reaction here, and you just divide 5 by 2, you'll get a 2.5 kilonewton. I'm gonna skip writing the units, it's just pain. So it's 2.5 here. Okay, here you have this distributed load on top, and it's 3 kilonewtons over meter. Yes, and what do I have here? I have a reaction here. Let's call this AY, and I do have a reaction here. Let's call this BY. And remember, I do have a reaction here in the x direction, but since there are no forces in the x direction acting on the beam, this will not come to play. Okay, here's the thing. You should know what's going on inside this hinge. So let me explain a little bit about the hinge. Okay, at the hinge, if you separate or you take off the hinge of the beam, you will have some internal forces, maybe are like this. This is what's going on inside the hinge, and these two forces are equal in magnitude and opposite in direction. So from this concept we can apply it to the 2.5 here. So this thing is the same as the 2.5, which is right here. So this force is 2.5 to keep this hinge in equilibrium. Okay, so how do I introduce this 2.5 to the other segment? Because I have to put something here representing this internal force. The easy way to do it is just to place a point load here, which is equal to 2.5 kilonewtons. And now on the left we have a beam that we can solve the reaction, or can find the reactions by the methods of applying the equilibrium equations. Okay, let's try to do this very quickly. So I have the summation of the forces in the y direction are equal to 0, and assuming the upward forces are positive, so that gives me AY plus BY, these are the forces from the bottom, should equal the forces from the top. What do I have from the top? I have the 2.5 I introduced, plus I have the concentration of the distributed load here, which is equal to the magnitude 3 multiplied by the whole length of the distribution, which is 6 meters. Okay, so it's 3 multiplied by 6, and if you do this, you will get an answer of 20.5 kilonewtons, and that will give you the first equation. So AY, again AY plus BY will equal 20.5. Now remember, the three equations of equilibrium are the summation of the forces in the x direction will equal to 0, and again we didn't use this one because we don't have any forces in the x direction. Then summation of the forces in the y is equal to 0. Then that's the equation we just did. And the third one is summation of the moments about a point, and let me assume that this is my positive direction, should be equal to 0. So now I need to take the summation of the moments about any point on the beam. Okay, one of the best points is this and this. Why? And of course this one, because, well, let me take this back. These are better actually. Okay, for this one, if I take the summation of the forces, the moments above this point, or I calculate the moment above this point, this unknown force will not be introduced into the equation because the line of action of the force passes through the point of rotation, or the point I'm interested in. And the same thing applies to the point B. So let's take the summation of the moments about point A. So let me write down this thing like this. So it says summation of the moments about point A should equal to 0, and the counterclockwise is the positive direction. Okay, so the way I usually do it, I start from the far end and work my way through all the way to the point A. So I do have a force here, so it's a force times distance, so it's 2.5 multiplied by the distance between the 2.5 and the point of rotation, which is 3 plus 3, that's 6. Now before I continue, I do have a plus here which represents the sigma, but I need to assign or study the sign of rotation here. Okay, the rotation is going this way, so it's clockwise, so it should have a negative sign because I assume the positive sign goes only with the counterclockwise. Okay, now plus, let's take the second force. Okay, we don't have anything here yet, but let's try, for example, BY. So we do have BY multiplied by the distance, which is 3 in this case, and before I continue, I should see the sign of rotation. It's rotating this way, so it's positive. Leave it this way. Okay, am I done? No, I still have the concentration of this force. The concentration of this force from top should look something like this. It's the distribution on 6 meters, so at the middle I will have a force, and this force will have a magnitude of 3 times 6, which is 18 kilonewtons. So now we can forget about this distributed load and try to imagine just the concentrated load. So it's 18. So again, let me just to be consistent with colors, here we have a plus sign for the summation, and we open parentheses, we have 18 multiplied by 3, so it's 18 multiplied by 3. And the sign, the rotation, oh, it's negative sign, so it should have a negative sign, and that should be equal to 0. So let's look at this equation again. We have 2.5 times 6 for negative sign plus by times 3 plus negative 18 times 3, and if I solve for by, I'll get a by will equal to 23 kilonewton. You can do this on your own. Okay, let me scroll down a bit here. Okay, scrolling down. Okay, now I do have by or ay plus by equals to 20.5. Now I have ay plus 23, I just solve for that, equals 20.5, and from this one we get that ay will equal to negative 2.5 kilonewton. So now we have ay and we have by, which is 23 kilonewtons, and what else do we have? Okay, let me scroll back up. Okay, we do have this reaction right here, which represents the cy, and this reaction which represents the dy, which are equal to 2.5. So, and cy equals dy equals 2.5 kilonewton. Now I do have all the reactions. All I need is to draw the shear and bending moment diagram. Okay, let's try to do this. Okay guys, after some cleaning up, here I summarized the results, and I cleaned up the space for you guys so we can go ahead and draw the shear force and bending moment diagrams. Okay, we notice here that in the summary I have ay negative 2.5, so it's negative pointing downwards and it has a value of 2.5. by is 23 going up as a reaction. cy, see I put a mark here saying that cy, you don't, because it's an internal hinge, or I'm sorry, it's not an internal hinge, it's not a support, so you don't put any forces on the diagram right here, but it will come into play once we try to understand how we do the shear and bending moment diagrams. And at dy we have a 2.5 going up. Okay, so let's try to do this. Now we do have cy, or I mean ay going down with a value of 2.5, so it should go like something like this, going down 2.5. Okay, if I scroll down just a little, alright. Now, what happens at point B? Do I have the force, the shear force, shear diagram going up or going down? Okay, I notice here that between A and B, I do have a distributed load right here that goes down 3 kilonewtons per meter. So, how many meters from here to here? From A to B is 3. So if I'm going 3 kilonewtons per meter, okay, and I'm gonna do this 3 meters or 3 times, so the total number is, you guessed it, it's 9. 3 times 3, so it's the load multiplied by the distance will give me the final value right here. So should I go, for example, here and say it's 9? Wrong. It's 9, correct. If I started from 0, yes, it's 9, but I'm starting from 2.5, so I add 9 on top of this 2.5. So let me quickly erase this. So it's from here, it's gonna go in a straight line, and hopefully I can do a straight line. Yeah, that wasn't bad. Okay, alright, so here we have a value. The drop from this point to this point is 9, but the total drop should be counted from here all the way down. So it's 2.5 plus this 9, so I have 11.5 5, and of course it's a negative value. Okay, so what happens here? Now I'm at 11.5 in the negative. Okay, do I have any forces up at point B? Of course, I do have the reaction. Alright, so the force of this reaction will just basically push me up a value of 23. Again, 23 from this point. So this distance is 11.5, so I'm gonna be pushed all the way here to 0. I was pushed 11.5 and another 11.5, because the total 11.5 and 11.5 will give me 23. Okay, so I'll end up going here. So I'm pushed, the total length here, or the total pushing, is equal to the reaction here. Alright, so it should look something like this. Now I use the same exact logic. What's going on between B and C? Again, I'm gonna drop from 23. I'm gonna drop how many? Okay, 3 times 3, that's 9 from 23. But again, this is not the 23. Okay, I made a mistake. I shouldn't be 23. The whole thing is 23. This thing is 11.5 in the positive. The whole thing, the whole jump is 23. I was at negative 11.5 plus 23. I'll get positive 11.5. So I'm gonna drop to this point like a straight line like this. Okay, and what is the total drop? The total drop from here to here is 9. Why? Because 3 meters, 3 kilonewtons per meter. Okay, but what about this distance? Well, it turns out to be a very good number that we will see right now. It makes sense. So I'm dropping 9 from here, so I stop here for a second. Now, what is my next point to study? Is this point. What's going on in this point? I do have a force, as you see, right here, 5. So between this point and this point I have no forces, so I continue in a straight line. What happens here? This 5 will bang me down. So I'm here. The distance, I'm dropping 9 from 11.5. So what is left here? What is left here is 2.5. So I'm here at 2.5. This distance 2.5. So I'm here at 2.5, getting banged by this 5 kilonewtons. So I'm gonna drop 5. So it's 2.5 and another 2.5. So the total drop here is 5. So what is this point? I was in positive 2.5. I dropped to negative 2.5 exactly. Okay, now what's going on between here, between this point and that point? Are there any loads here? No, so I just keep on going straight. Alright, so if I go straight this way, what happens at this point? You see this is a 2.5 pushing me upwards, so I should go 2.5 and voila, I am at 0 again. So that's a good checkpoint. If you start from a 0 and end up of a 0 and on these kind of beams, you should be okay. So that is the shear diagram. Okay, let me clean it up a little bit just so we can see what's going on. So I'm done with this. I think you get the idea here. And this one should go, and the dropping value, you know it by now. Okay, 2.5, blah blah. Okay, so I think we're ready to go to do the moment diagram. Okay, what is the best way to do the moment diagram? There are a couple of tricks you can do. Okay, but first, what are the points that you need to know the moment at? Okay, let me try the green. Okay, green, how's the green? Yeah, it looks okay. Alright, So we have a roller here, or a hinge here, and we have a roller here. So the moment here should be 0, the moment here should be 0, since they are at the end of the beam and they don't have any contribution at the moment. They don't resist any moments. Okay, so what is the moment value here? And do you expect it to be positive or negative? Okay, what you can do is look at the shear diagram. The whole shear diagram between this point and this point is in the negative side. The area of the shear is in the negative side. So I'm expecting my moment to be somewhere here. But what is the value I should put for this moment? It's exactly the area of this diagram. And what is the area of this diagram? If you do this correctly, well, let me try to do it quickly. Okay, we have something like this, right? And it's 11.5 without the negative signs for now. It's 2.5 here. If I remember this correctly, and this distance is 3, I take the average of this and multiply it by this. Okay, so it's 11.5 plus 2.5 over 2, that's taking the average, and then multiplied by 3, that should give me 21, and that is correct. So here we have a negative 21. I'm just putting the values for now. Okay, what is the other point I need to worry about? It should be this one. And the value of the moment at this one, and remember, this is the hinge. This is where we have the hinge. Some of you will say, well, you already know the value of the moment here. Just let me explain it, how we can prove the value you have in mind, if you know anything about hinges. Okay, the old-fashioned way, just to do it the same way, it's the area of this shear and moment diagram. Okay, or shear, I'm sorry, it's of the area of the shear diagram here, plus it's a plus, it's a positive, and we shouldn't forget to add it to the previous area. We don't just calculate it and plug in the number. We should add it to this area, because the moment at any point is the summation of the areas from the beginning until the point you are interested in. Okay, if we do this, if we do and calculate this areas, okay, let's draw it here. So what do we have here? We have 11.5 and we have 2.5. I think we've seen these numbers before, right? It's right there. These areas are the same. So this area is 21, but what is the difference? It's a positive 21. And if we add it to a negative 21, we will get a 0 here. So this value is 0. So we start with a 0. At here we have negative 21, we have a 0. Okay, now what about this one? Alright, at this point it's the summation of all the areas from here all the way to the point of interest here. Since we know that the summation of these two areas are 0, so all I need is just to calculate this area, which is 2.5 multiplied by the distance, which is 2.5, I believe. Is it 2.5 by 2.5? Let me double check the question I have. What is it? Is it 2. No, it's 1.5. I'm sorry, it's 1.5 by, this is 1.5. Alright. Let me grab my calculator here. So it's 1.5 times 2.5. That will give me 3.75. So the area here is, this area here is 3.75. So we add this to this and to this. Again, since this and this cancel out, so we end up having 3.75 at this point. So it's right here, 3.75. And at the end it's a 0. You can check it. you calculate this area, which is 1.5 times 2.5 again, but it's a negative value, so it's negative 3.75. and if you sum up the areas, these areas cancelled before, and we have now positive 3.75 and negative 3.75. They cancel, so they add up to 0. So we start with a 0, go minus 21, go back to 0, positive 3.75, and back to 0. Now we're ready to draw the bending diagram. How does it look like? Okay, since or let me write it this way. Okay, just for you to remember it. This is the V and this is the M. If the V was a straight line, the M is straight line increasing or decreasing. It doesn't really matter, but remember it's a straight line. And if V is increasing or decreasing, we have concavity. Alright, so let's see. Between this point and this point on the V, we have a decreasing, or just, it's not a straight line, so we have concavity. So it looks something like this. It's not a straight line. Here again, between this point and this point only, from here to here, it's decreasing, so it's concaved like this. They should be like one point here. Now, for this one, it's just a straight line. So the moment from here to here is a straight line like this, and from here to here, since the V is a straight horizontal line, so we have it like this, a straight line. So these are two straight lines, and these are concave down curves. And this way we have, I know it's I apologize, it's a little bit messy, but this way we have the V diagram or the shear diagram and the moment diagram. Okay, I really enjoyed answering my subscribers' questions. If you have any questions that I can do, please don't hesitate to contact me, and thank you for stopping by.